here. How about that? All right, so day 2 on linear stuff, angle stuff, sectors, lots of stuff with angles today. Arc length of a sector. A sector is a portion of a circle that includes 2 sides, which are the radii of the circle and an included central angle. So that shaded area right there is called a sector. It's a piece of pie of the circle. That would be a large piece of pie, but that would still be a piece of the pie. Thanksgiving coming up. Is anybody going to eat that large of a piece of a pie? Like, yes. Not all at once, because that would be...
Depends on the pie.
Yeah, depends on the pie. And all at once, you look like a pig if you took that. But if you had 3 small pieces, then you're less of a pig, right? Right? I mean, you can't grab a piece of pie that looks like that. You got to break it up into pieces. You're just going to just take the whole thing. Or do the thing where you cut a small piece out and then take what's left to eat. All right, back to arc length of a sector. So we want to know this L, how long is the arc length of the sector? Let's back up a second. We didn't say this. I said it briefly on Friday, and that is the definition of theta in radians is that arc length divided by r. Like, that's literally the definition of what a radian is. It's how long the arc length is divided by r. And so you can kind of rearrange things, and L is r times theta. So there's the formula for the arc length. By the way, you could check that with a full circle, because you know how far around is a full circle. Pi r squared is the area of a full circle. 360 is the degrees around. What do we call the length? But what do we call? Yes, you're right. What do we call it though? The length all the way around. That's what I'm looking for. Circumference. So in theory, you already know that the circumference is 2 pi r, but that matches the arc length formula because the r is right there, and the theta is 2 pi. So you could sort of check, or maybe even come up with that formula with, match it to one you already know. The circumference is a specific application of the arc length formula. It's another way to say that. Because the angle is 2 pi all the way around, and r is the radius. Okay, all that to say, length equals r theta. Theta has to be in radians, so be careful. If it gives you a theta in degrees, we'll change it to radians and then do the problem. Determine the length of the arc of a sector with radius 10, central angle pi over 3. Well, it's the first one, so of course it's as easy as we can get it. The radius is 10. The angle is pi over 3. So that arc length is 10 pi over 3 centimeters, right? Because it's a length. And theta doesn't really have a unit, like the angle in radians is unitless. So centimeters times no units is still centimeters. Number 2, determine the length of the arc of a sector with radius 3 feet and a central angle of 240 degrees. Well, let me do it wrong first, and if you're paying attention, you'll catch the wrongness. The length is, so you're just kind of cruising along. Radius is 3, angle's 240. And yeah, it needs to be in radians. But again, if you're not paying attention and you're just kind of cruising through and not really understanding the formula, 3 times 240 would be 720. So think about what you just said. You got a radius of 3 feet, angle of 240, so that's what, more than 180, so it's like that. You're telling me that arc length is 720? Oh, come on, that doesn't make sense. And the reason it doesn't make sense is you're not supposed to use degrees. So if you're paying attention, you will catch that, because you'll get an answer that doesn't make sense. Now, if we change 240 to radians, let's see, we'll put degrees to cancel. 24 over 18. I can divide by 6. That gets me 4 pi over 3. Okay, so now I can do L equals R times theta. Radius is 3. Angle's 4 pi over 3. So 4 pi feet. Pi is 3-ish, so that L is 12-ish. That makes a whole lot more sense than 720. So again, you got to be in radians. If you forget to convert to radians and your brain is turned on, you will recognize that something is wrong. Hopefully. L equals R theta. That's the arc length formula. All right, area of a sector. So kind of the same process, same thought process here. Right, there's my sector. There's an R, and I want to know the area of that sector. Well, we can come up with a formula, but I think coming up with the formula is more helpful than the actual formula. And by that I mean, let's just do like a ratio of the part to the whole. So, and we'll do angles and areas. So the angle, I filled that in too much. The part of the angle is theta, right? Like that's the part we're looking for. What's the whole angle? Like if I go all the way around the circle in radians, 360. In radians, 2 pi. The area is what we're looking for. What's the area of the whole thing? Pi r squared. So I memorized that because it's not really memorized. I can come up with that. Now there is a way to arrange things here. If we multiplied both sides by pi r squared, theta over 2 pi times pi r squared, we would get, let's see, the pi's would cancel, theta over 2 times r squared. So that's the memorize the formula method. Theta over 2 times r squared. I prefer to think of it as like a ratio. Part of the whole times pi r squared. So if you got half the circle, well then you do half of pi r squared. If you got 1/3 of the circle, you do 1/3 times pi r squared. So either one of those is fine. I think this one's simpler, but you have to memorize it. This one feels more complicated, but in my mind that makes more sense. Like that's the easier concept way to go. So they say the same thing, they just don't look alike. Number 3, determine the area of a sector with central angle 2 pi over 3 and radius 4 inches. Okay, I'm going to do it sort of the concept way. So 2 pi over 3 out of 2 pi is how much of the circle we're talking about. Sorry. 2 pi over 3 out of 2 pi is the part of the circle we're talking about. And then times pi r squared. To me, that's maybe a more complicated formula. but I don't have to memorize the formula. I can remember that one. So let's see. 2 pi over 3 times 1 over 2 pi times 16. So I got to put all that stuff together. Careful with the pi's. 2 pi cancels. And I'm left with 16 pi over 3 inches squared. That's how I would work that problem. The part of the whole times the whole area. If you memorize the formula, granted it's a little bit quicker, I think. 2 pi over 3 over 2 times 4 squared. The 2's cancel and you end up with 16 pi over 3. So either way, the formula's quicker, but then you got to memorize the formula. The part over the whole, to me, makes more sense. It's less memorizing, it's more understanding, but maybe it takes more work. So it's kind of up to you. Do you want to memorize another formula, but make your life a little shorter? Or do you want to not memorize and then have to deal with a little bit more work? I prefer not to memorize things, but you can do it either way. Number 4, determine the radius of a sector with central angle 3 pi over 4 and area 24 square centimeters. Okay, so again, I'm going to kind of continue with the concept way and the formula way. The area is 24. The central angle is 3 pi over 4 out of 2 pi. And then the whole area would be pi r squared. So I got to figure out what r is. Well, let's see. This would be, pi's will cancel. So 3/8 times pi r squared equals 24. Right? Either keep it, change it, flip it, or know that the 4 and the 2 multiply. Multiply by 8/3. So that would be 64 equals pi r squared. That's a convenient number for what we're about to have to do in a minute. Like square root both sides. So 8 over the square root of pi. Oops, centimeters, not inches. I wonder if that area was supposed to have a pi in it. It would have made this a little easier. But. Formula way. Area is 24. Theta is 3 pi over 4 over 2 times r squared. So let's see, that would be 48 equals 3 pi over 4. If I multiply by 4/3, I get 64. And of course I get the same thing. Pardon? Are we going to have to do proofs? Is that what you said? Don't throw anything until I finish the answer. Which means the answer is yes. But they're not like geometry proofs. Oh my God. I think they're a lot easier than geometry proofs. And they're not till next semester, so don't panic yet. Save your panic till next semester. And even then, most students find them much better than geometry. What prompted the question out of this? Was it just random, or was there something in here that looked like proofy? PTSD. Fair enough. Number 5. Determine the central angle of a sector with radius 3 and area of 30 square inches. Okay, so the area is 30. The central angle over 2 pi times pi r squared. Like that's, oh, we know the r though. Radius is 3. Again, that's the concept way that I'm thinking about. The area is the ratio times the whole area. And then this is kind of nice. The pi's cancel. I would multiply by 2 and then divide by 9. So 60 over 9, although that reduces to 20 over 3. And that doesn't have a unit because it's the radians, and or if you like carried your units through, you'd have inches squared over inches squared, and they would cancel out, which is what we expect to happen for radians, because it's not, I mean, it's a measure of the angle, but it doesn't have a unit. Okay, now for the fun stuff. Linear speed and angular speed. Yeah. Let me pause the video. Okay, so back to the notes. That was good. You guys nailed it. All right, you were arguing and not happy with each other, but you had the right answers. Consider a particle moving along the arc of a circle with a radius r. So that pink post-it note on the outside there. Linear speed measures, this is what you were saying, distance over time. Distance over time. Which was sort of the basis for Michael's case for pink being faster, because it was more distance, because it was a bigger circumference. Yes. Examples of linear speed. So you tell me, what are units of linear speed? Meters per second. Miles per hour. Sure, kilometers. We'll even go. Let's go crazier. Kilometers per day. Who knows? I mean, if you're hiking, that would be an appropriate unit, right? Like, how many miles did you walk today? Angular speed measures. Let me back up a second. I'm going to put a little delta in front of that distance. Change in distance over change in time. Angular speed measures change in angle over time. So examples of units of angular speed. RPM.
Is that change in angle?
Yes. So revolutions per minute, which is the same thing as RPM. That's sort of the standard one that we're used to. But in physics and PreCal, we're more likely to see radians per second. But RPMs is, that's what, like the standard thing, if you're the speed of a pump or something is in RPMs. Your engine, the other gauge that you don't know what it means, right? Like, you know what the speedometer gauge is telling you, but that RPM gauge, what the heck is that telling you? Well, it's telling you the rotations, not of your tires,
I don't know why sometimes.
but your engine. All right, is conventional called linear velocity with a lowercase v, right? So we're not changing what you already know. Like little v is velocity. We're good there. Is conventional called angular velocity with a lowercase Greek omega, that little, like a script w. That's what it looks like. A script w is omega. That's angular velocity. Okay, so for a particle moving at a constant speed along a circular arc of radius r, L is the arc length traveled in time. This is a lot of words. Let's just back up here. Velocity is, let's just back all the way up, change in distance over time. And the distance we're going through is that L, right? That arc length. So this is the connection to what we were just talking about. So arc length over time. But arc length is r theta over time. So there's sort of two equations. Velocity is distance over time. That's your normal equation. You're used to that one. But if the distance is r theta, we could sort of write that as r theta over time. So that's kind of the same equation. I don't want to say there's two different equations. It's the same one. One just uses the fact that L equals r theta. The arc length is r times the angle. Next box. For a particle moving at a constant speed along a circular arc of radius r, if theta is the angle in radians corresponding to the arc length L, the angular speed, this is a lot of words, but we already said angular speed is change in angle over time. Well, the angle is the theta, so theta over time. That hardly deserves its own box. It's like, yes, the angular speed is radians per second, or revolutions per minute, or even degrees per second. Now, we're going to kind of put these two things together. We said V is equal to R theta over T, right? Because R and theta make L. R theta make L. But if we kind of regroup the variables, instead of looking at the R and the theta together, if we took the theta and the T together, right? Like I didn't do anything fancy there. I just sort of regrouped who was with who. What's theta over T equal? Omega. So velocity is equal to R times omega. Velocity is equal to R times omega. It's probably the most used of the formulas on that page. Pause one more time and look at that wheel again. That's all I know. That's about all I know about inertia too. Example. The second hand of a clock is 10 centimeters long. Find the linear speed of the tip of the second hand as it makes one complete revolution around the clock. Give your answer in units of centimeters per second. Okay, so velocity is R times omega. That's how I would start it. Mainly because I know R, that's 10. Omega, I don't really know omega. How fast is it rotating? So how fast is the second hand going around the clock? Okay, I like per minute, right? Because it takes 1 minute to make it all the way around.
Oh,
How far is it in radians or in angle? How far is it all the way around? 2 pi. So I can say the angular speed is 2 pi per 1 minute because it's the second hand. It makes a full trip every minute. Give your answers in centimeters per second. Okay, so I need to change this. Minutes to seconds. Let's see, 1 minute is 60 seconds. So pi over 30 radians per second. I hesitate to even write radians because radians is kind of a non-unit, so I don't need to write it. So 10 centimeters times pi over 30. I'm going to keep writing it to show you what happens if you keep it in there. So my answer is pi over 3. But what's my units? So do I include the radians or not? Right, I don't because the radian is a non-unit and it really wouldn't make sense to include it here. So just centimeters per second. So that's weird about radians. You can throw it in there if it makes sense. Like if you're talking about angular speed, maybe it makes sense to include radians. But if you're talking about linear speed, I don't want radians in there. So let's just do centimeters per second.
Be very close to 1 centimeter per 1 second.
That's true, that because pi is 3, so that'd be about 1 centimeter per second. Which, I don't know, I'm looking at that clock over there. If that second hand was extended all the way out, then it'd probably be moving the tip of it would be moving 1 centimeter every second, give or take. I'd believe that. That second hand got stuck one time, so I cut it off, so it's a short second hand now. Number 7, the blades of a wind turbine are 116 feet long. That sounds like an R already. The propeller rotates at 15 revolutions per minute. Find the angular speed of the propeller in radians per minute. Okay, so I need to do I've got an omega, but I've got the units that I don't want. So I like the minutes. I don't want the revolutions. Revolution to radians. How many revolutions are in a radians, or vice versa? What's a revolution mean?
One full rotation.
One time around. So 1 time around is 2 pi radians. So my omega then is 30 pi radians per minute. If you really, you can throw out radians anytime you like. I mean, it asked for it, so we should probably put it in there. But since it's a non-unit, you could also say 30 pi 1 over minutes. Find the linear speed of the tips of the blades in miles per hour. Okay, so V equals R omega. I've got my R, 116 feet. I'm trying to set this up nice and neat because I know more changes are coming here. Times 30 pi radians per minute. But we're headed toward velocity, linear velocity, so I don't need radians. I'm going to just throw that out. And now I've got just the good old chemistry problem and physics problem of unit conversion. Miles per hour, so minutes to hours. So I want the minutes to cancel. There's 60 minutes in 1 hour. And then there's 5,280 feet in 1 mile. And I would really like to know how fast that's going, so I could. I mean, that's my answer, whatever that is. But I want to know how fast is that thing moving. Looking for a calculator. So 116 times 30 pi times 60 divided by 5,280. 124 miles an hour. Which seems really fast, but if that's 100 feet long, the further out we go, the faster we go. So faster and faster it goes, the further out we are. Because V equals R times omega. Okay, so be careful. Omega is angular speed in radians per second usually. Here's the summary in 2 lines here. V is the linear speed. Distance over time, or L over T, or R theta over T, or what we usually use is R times omega. Alright, the assignment is worksheet number 2. And it specifies on there some with calculator, some without. Because we usually if we want linear velocity, we don't want that in terms of pi. We want a number, how fast is that fan blade moving at the very end. So the worksheet will tell you whether to use a calculator or not, like by problem, per problem.